Okay, so continuing on from yesterday, we still have two formulas, acceleration formulas to get through. All right, so I'd like you to write this question down, and we will go through it together here in just a sec. All right, so let's have a look at what our givens are for this problem. Okay, so we have a speedboat that slows down at a rate of 5 meters per second. I like how that one's worded. Okay, because that's a more accurate or realistic way to describe the acceleration of an object. Okay, that means its acceleration is negative 5.0 meters per second squared. Okay, and it comes to a stop. What did they just tell me there?
Zero.
What's zero? Final velocity is zero, right? Okay, the process takes 15 seconds. Find the displacements. Okay, what formula am I going to use? Right, I'm going to use this one. D equals VF times T minus 1/2 AT squared. We talked about that one the other day. On a velocity versus time graph, this formula calculates this whole box and then subtracts this triangle to leave us with the area under the line, which is the displacement of the object. Okay, so what we want to do here is just plug in our numbers. It's already set to solve for D. Okay, so we just have to plug in 0 times T. 0. All right, I got to write the 0 there though. It doesn't go away because I got to subtract something from it. Okay, 0 minus 1/2 times negative 5. This is where those negatives are crucial. Okay, times 15 squared. Okay, so we got 0 minus 0.5 times negative 5 times 15 squared. All right, that gives us that this thing is going to travel 562.5 meters in a positive direction. I only have 2 significant digits, so I will be looking at 5.6 times 10 to the 2 meters forward. Okay? Because last time I checked, when you're slowing down, you still move forward. Yeah. Okay? You might be accelerating backwards, but you're still moving forwards until you stop.
I do have a question now.
Okay?
How does drag racing work? There's a lot of physics that goes into it, right?
There is a lot of physics that goes into it.
I was just thinking about that.
So there's a lot of maximizing friction, maximizing like work, energy theorem, torque, all of that kind of stuff to produce the accelerations that you see in drag racing.
So another one.
Okay.
If you have the mass of the car, could you
Yeah.
figure out the horsepower?
You could, yes, if you figured out how much energy was required to accelerate it down the strip, and then took the time and went work divided by time, joules per second would give you, watts. You'd get it in watts. Then you'd have to convert it. 500 and some watts in a horsepower, something like that. It would be involved.
Yeah.
Because you'd have to subtract all the drag and all that other stuff. Yeah. But you could do it.
Is that why graphs with cars doesn't really work because of the drag as well?
Yeah, partially, because as you go faster, drag increases.
Yeah.
Yeah. The faster you go, the more friction works on you, because the harder you push on the air, the harder the air pushes back. Yeah.
Is that why like Formula 1 cars are so aerodynamic?
That's why anything that has to go fast is so aerodynamic. That's why when they run planes like the SR-71 Blackbird, when it flies, when it lands, they have to be careful getting the pilot out because the skin of the plane is so hot it would burn. Okay, so that formula making sense?
Yes.
Manipulations of that formula are very much like its sister formula that we looked at yesterday. Okay, once again, you'd never be asked to calculate time in this formula unless VF is 0 in this case, yeah. Okay, because obviously T is in 2 places, right? But if VF were to be 0, okay, then all you'd be left with would be this.
We have grade 12, last name starting H through L. Please come to the cafeteria to get your picture taken.
Okay, and then of course we would have to retain the negative, right, and make sure that we move it around as well. Okay, I would like you guys to try those two questions. Yeah, they use that formula. Okay, and keeping in mind with number 1, it does ask you to calculate time. Peter and Keegan, I tried to make a point this morning about talking and when I'm talking and paying attention, but I feel like I wasn't heard either day right now. Sorry. Okay. In number 1, you're being asked to calculate time, but it does involve something that comes to a stop. So VF is? Okay. Watch out for the kilometers per hour in number 2. All right, so I know we talked like a little bit about Top Gun Maverick yesterday, but this is another like Top Gun Maverick kind of question, okay, where you've got a plane coming to rest on an aircraft carrier. Obviously, an aircraft carrier is not long enough to land a plane conventionally, okay? They can't slow down quickly enough. So they have these cables that are strewn across the deck, okay? And they're attached to these big steam-powered like motors. Okay? And so what they do is when the plane catches these cables, okay, the cables pull and resist, and actually they catch on a hook that dangles from the bottom of the plane. Okay? The stop is quite violent. Okay? It is like it throws the pilot into their harnesses head forward. Okay? Like they probably have to have an onboard chiropractor. Okay, on the aircraft carrier, okay, given the violence of the being shot off the deck by pretty much the same mechanism, okay, and stopping it in the same way. All right, so we know that they have to come to a stop, so we know that VF equals 0 meters per second. Okay, we also know that it has to do that in 150 meters. It's actually less than that, but we'll say it's 150 meters. Okay, and the acceleration is negative 15 meters per second squared. That's greater than gravity. Okay, so imagine being thrown into your harness so hard that it feels like there's 1.5 of you. Okay, instead of just one of you being thrown into the harness. Okay, it's hard. Okay, so our acceleration is negative 15 meters per second squared, right? And oh shoot, we're almost out of time. Okay, so we would solve for t. So it would be d equals negative 1/2 at squared, okay? And we would just be solving for t here, so we divide both sides by negative 1/2 of a and square root. And that'll get us our t. All right, we'll talk more about that one on Monday. Hey, plan for next week, we got a lab on acceleration. I think I have a plan for Tuesday. Okay, so we'll be breaking up all the seat work, okay, with the lab. Okay, so let's look at our second one here. So we've got the 68 Corvette took 6.2 seconds to accelerate to 160 kilometers per hour. That's impressive, because how fast in miles an hour is 160? 100 miles an hour, okay? Like, there's a lot of cars that can't go from 0 to 100 kilometers an hour in 6.2 seconds, okay? This was a powerful machine. Okay, so our time is 6.2 seconds. Our initial velocity is unknown. They don't tell us. I can't assume that it was 0 because they don't tell me that. Okay, but it does accelerate. Okay, to 160 kilometers per hour, which I have to convert to meters per second. So 160 divided by 3.6, 44.4. meters per second, okay, and it travels 220 meters north in that time. Find its acceleration. All right, well, I got to use this formula again. D equals VF times T plus 1, or not plus, minus 1/2 AT squared. All right, so first thing I'm going to do, since I want to isolate A, is subtract VFT over to this side, so D minus VF times T equals negative 1/2 AT squared. I want to get A by itself, so I'll divide by 1/2, negative 1/2 of T squared. Okay, and now I'm solving for A, so I just have to plug in my numbers here. It was 220 meters minus 44.4 times 6.2, okay, divided by negative 1/2 times 6.2 squared. right? And when we plug all that in, we should get 2.9 meters per second squared. Okay, it should come out positive when we plug it in. Okay, because we're preserving the negative on the bottom. This will produce a negative number on the top. Okay, so we got time here, we'll just plug it in. So 220 minus that times 6.2, okay, gives me negative 55. If I divide that by negative 0.5 times 6.2 squared, okay, I get 2.9 meters per second squared, it's positive. Okay, for next week, on Monday, we're going to continue on. We still have one more formula to do for acceleration, and then we'll work on acceleration on Monday. Tuesday, we're going to do a lab on acceleration, okay, and velocity versus time graphs and things like that. Wednesday, we'll probably finish up acceleration and move on to projectile motion. Okay, Thursday, Friday, projectile motion. Okay, Monday, Tuesday, projectile motion. Wednesday, I'll do a unit exam review. Thursday, October the 6th, unit 1 exam. Right, we are coming up on the end of this unit pretty quickly. Okay, so that's where we're at. Plan going forward will be like so. Questions from you guys? Okay, if you want any feedback on that graphing lab, your absolute last chance to do that would be Monday morning, just after 8 o'clock. I do have help Monday morning, just after 8 o'clock. Okay, so that's not going to give you much time to do any editing. Okay, if there's anything to do. So make sure you're working on that lab report over the weekend so that it's ready to hand in on Monday.